Awesome. Derek, thanks for joining us today. I'm super excited about this. I think we'll have one or two more dings in the next few minutes, but that's fine. Someday, maybe when I get to 4 years of running this group, I'll figure out how to turn off the dings on the Zoom.
Yeah.
Yeah, I'm really excited about this talk. I started out my PhD working with Stavros doing model checking related stuff and learned everything I know about model checking. So it's cool to see work coming out of that lab. And in particular, I think that uh, synthesizing anything distributed is like astonishingly hard. And so I'm personally very excited to see kind of how you've attacked this problem. So thanks for joining us. And yeah, the stage is yours.
Awesome. Yeah, thanks for this opportunity. I'm really excited to talk to you guys about efficient synthesis of symbolic distributed protocols by sketching. So this was our recently accepted FMCAD paper. So I think we can just hop right in if now is the time, or should we wait for more dings?
Yeah, I think we can go for it.
All right, let's do it. Okay, cool. So I think we'll just start off by setting the stage and talk about some of the contributions of the paper. So we're advancing the state of the art in the automatic synthesis of verifiable distributed protocols. In particular, we're looking at distributed protocols that have a symbolic representation in the widely used language TLA+. So just to contrast this with some other work in distributed protocol synthesis, a lot of that work deals with kind of explicit state models. Think like label transition systems or just like DFAs. So our systems are symbolic and they're not just some like toy language. This is like a language that people actually use. The systems that we look at are parameterized. So an example of a protocol parameter might just be like the number of protocols, or sorry, the number of nodes participating in the protocol. Some of the protocols have state variables with infinite domains. We test our technique on a suite of 8 benchmarks. We're able to synthesize non-trivial protocols. For instance, we have a reconfigurable Raft variant benchmark that we look at. And we're also able to synthesize some non-trivial expressions. For instance, this expression here is quite long. It involves quantifiers. It involves this custom operator quorums. So this is what I would call a non-trivial expression. Our approach is to do sketching, and we use syntax guided synthesis, counterexample guided synthesis. So these are things that we'll talk about today. And then kind of at the heart of our technique is this fast grammar enumeration procedure, and it uses semantic equivalence reduction. So that's what we're going to be talking about today. And we can just start by talking about distributed protocols a little bit. So as many of us probably know, these protocols facilitate disparate processes working together to solve some problem. Examples include two-phase commit, consensus, sharded key value stores, etc. The applications are pretty broad. These things are seen in communications, data storage, finance, transit. So that is to say that they're ubiquitous. They're kind of everywhere. They back a lot of very important systems. So when they go wrong, people can't talk to each other. They can't stay in touch. Data is lost. People lose money. And, in the worst case, people could die if, the distributed protocol on the back end of an airplane doesn't work properly. And despite all of this, they're really hard to reason about. And this motivates us to kind of model them formally. And this allows us to state properties about them and then prove those properties using formal verification. And then the problem that I look at is formal synthesis. So kind of in some sense, skipping or making the modeling aspect of formal methods shorter in some sense. So instead of starting with a model and a property and proving that the model satisfies the property, we're essentially just going to start with a property and then automatically generate a model that's correct by construction. Cool, so now we can talk a little bit about protocols in TLA+, how we model them. On the right is kind of an excerpt of a TLA+ protocol, but for the talk, we're just gonna kind of treat this thing like it's a a full-blown protocol that we might be interested in. Now, as I mentioned, TLA plus, it's like this widely used symbolic language for representing distributed protocols, concurrent programs, things of that sort. And I say that it's symbolic because on line 2, you see this declaration of vars. So again, these systems have state variables. They're not like explicit state. So we're going to define a state to be an assignment to these variables. They're also symbolic in the sense that the initial states are defined by this initial state predicate. For instance, in this case, on lines 11 to 14, this initial state predicate indicates that the only initial state is the one where vote yes, go commit, and go abort are all empty. There's also a next state predicate. This is typically represented as a disjunction of actions. So on line 16, we see this action go commit. And then on line 17, we kind of see this family of actions, one for each node participating in the protocol, the vote yes action. And then just to go a little bit deeper, actions are a conjunction of a pre and post condition on the state. So a precondition is something that has to hold before the action is taken, and then a post condition is something that holds after the action is taken. So for instance, on line 4, we have a precondition. It says that in order for the go commit action to be taken, it must be the case that all of the nodes participating in the protocol have voted yes. And on line 5, we see a post condition. And this says that after we've taken the go commit action, we've sort of told all of the nodes to, well, go and commit. And you'll notice the use of the primed variable there. That indicates the value of the go commit variable in the next state of the protocol. These protocols are parameterized. So on line 1, we see this constant declaration node that designates node as a parameter of the protocol. And this is used again on line 17, again, to kind of parameterize this vote yes action. Yeah. So now we can talk a little bit about the semantics of these protocols. We can do that by talking about runs. So a run is just an interleaving of states and actions. And R is a run of a protocol if S0 satisfies the initial state predicate and if adjacent states in that run satisfy the action between them. And then for the duration of this talk, we're going to use this kind of triple to denote states of the protocol in all of the examples that we're giving. And I'll put reminders about this when we use it. But so here's an example of a run. In this run, initially all of the state variables are the empty set. Then the vote yes action is taken on node A. So of course, A is added to the set of nodes that have voted yes. And then the go commit action is taken. And so if we assume that node is just equal to the singleton set A, then this is a run of the protocol on the right. And then here's kind of a longer example of a run. So first A votes yes, then B votes yes, and then the go commit action is taken. And again, this is a run if and only if node is equal to the set A and B. And then finally, this is an example of a run which is not a run of any instantiation of the protocol on the right. In particular, it just doesn't satisfy that first state there does not satisfy the initial state predicate. Cool. Now we finally can talk about TLA plus properties. So TLA plus supports very general temporal properties. But for this talk, we're just going to focus on state invariance. Our synthesis tool also can handle safety and liveness properties as input. So just to give an example of some state invariance, this is a state invariant. It is satisfied by the protocol on the right. In particular, go abort is always the empty set. This is an example of a property which is not satisfied by the protocol. You can prove that this is not satisfied by the protocol with this counter example. So as soon as vote yes is taken, vote yes is suddenly equal to the set of all nodes. Okay, so now we can talk about the actual problem that we're solving. So a sketch is defined to be a TLA plus protocol with holes. And a hole is really just an uninterpreted function. So it's got a name, it's got some dependencies, and it's got a grammar where the terminals are those dependencies. As an example of a hole, that function, that uninterpreted function h has the dependencies go abort and n. And this might be a grammar that we would use for this hole. So this is the grammar that just generates standard set expressions over the terminals empty set, singleton set n, and go abort. A completion of a sketch is just a protocol corresponding to some choice of expressions for the holes. So just plug them in. And those expressions have to come from the grammars. And this finally allows us to state the protocol synthesis task, which is given a sketch and a property, find a completion that satisfies the property. And now just to give an example of a sketch and a completion. So this is the protocol that we've been working with, but as you can see, we've replaced on line 10 the expression there, and we've added a hole. So some possible completions of this protocol would be to replace that hole with the expression go abort or the empty set. And these correspond roughly to the protocol that we were looking at before. But if we replace these expressions, or if we replaced that hole with the expression singleton set n or go abort union n, etc., that would actually violate one of these state invariants that we looked at before. And again, that we can show a counterexample showing that these completions violate those properties. And this kind of suggests a certain approach to doing synthesis, which is counterexample guided inductive synthesis, or SEGIS. So at the bottom of the slide, we kind of have a sketch of that architecture. But the way it works is that the learner is going to suggest a completion. The verifier is going to check if that completion satisfies the property. If it does, we're done. We've found a completion that satisfies the property, so we've synthesized a protocol. But if the verifier finds that it doesn't satisfy the property, then it's going to provide a counterexample. And another job of the learner is to kind of use this counterexample to guide the search going forward. In the ideal situation, the learner will never suggest a completion that exhibits any of the counterexamples that it's seen before. And we use the TLC model checker as our verifier. This is kind of standard TLA plus tooling, so we won't talk too much more about the verifier, but we will go into more details about the learner. So on the right is kind of the rough architecture of our learner. It first takes the counterexample and hands this to the counterexample generalizer. And this is just going to encode the counterexample as a logical constraint. This will be a constraint in like propositional logic with like a theory of uninterpreted functions, basically. And the constraint checker is just going to keep around, it's going to accumulate a set of these constraints. And then the constraint checker and the grammar enumerator will work together. The grammar enumerator will just enumerate expressions from the grammar. The constraint checker will check those expressions against the accumulated constraints. And then we're only going to pass a candidate completion to the verifier if it satisfies those constraints that we've accumulated. And what this does is it allows us to avoid a lot of model checking calls, which is a very expensive operation. So we won't talk too much more about the constraint checker, but just to give a sense of what it does, it's really just plugging in the interpretation for the uninterpreted function and then evaluating. So it just works by simple expression evaluation, which is much, much cheaper than full-blown model checking. Cool. So we won't say anything more about the constraint checker, but we will talk about these other two components. In particular, we'll talk about the counterexample generalizer next. So we'll do this by example. Suppose we have this property that we've seen before, and we have kind of our running example that we've seen on the right. And let's say that we picked this interpretation for H as the completion, and it generates this counterexample. So I think the first thing to notice here is that we don't control any of the actions except the vote yes action, And within the vote yes action, the only thing that we have any control over is the whole H. So we're going to restrict our attention to that first transition because it's the only one that has the vote yes action. And we're going to note, first of all, that N is equal to A. And we're also going to notice that in the first state, the goAbort variable has the value empty set. Then what we're going to do is we're going to evaluate the whole that we chose, the expression that we chose for the whole. We're going to evaluate that expression using these values, and we're going to find that it evaluates to singleton set A. And this suggests a very simple constraint on future completions. In particular, we want to pick completions where H does not evaluate to singleton set A under these under this interpretation of the dependencies. And what this does is it makes sure that the first transition that we saw in the counterexample doesn't exist in any of the future completions. So of course, none of those completions can exhibit this particular counterexample. Just to maybe generalize those ideas a little bit, in general, we might need to disable at least one transition in a counterexample. So if we have like this counterexample where A votes yes, then B votes yes, because the vote yes A transition and the vote yes B transition are both controllable, it's sufficient and necessary to disable at least one of those transitions. And that will ensure that we never see this particular counterexample again. And then there are other cases, for instance, we might have more than one whole, right? We might have H1, H2. And so in general, these constraints are going to be like these disjunctions of disequalities. And those disequalities are computed by kind of plugging and chugging from the counterexample that we find. And then the constraint, it has size, roughly order holes times the number of holes times the length of the counterexample. But this is a very loose bound because not every hole exists in every action. Deadlock and liveness violations, which we're not going to go into too much detail, are more complicated. Because to repair like a deadlock, for instance, you can disable the transitions that lead to the deadlocked state, or you can add transitions basically in order to make that state no longer a deadlock state. In the case of liveness, if you have some cycle of transitions where no progress is made, then you can add some kind of fair transition to the protocol in order to escape that cycle. So that gives you a sense of how we handle deadlock and liveness properties and violations. But details are in our paper. Okay, now we can talk about grammar enumeration. So here's our figure from before, just so we don't lose our thread. And we're going to go over kind of 3 ways to enumerate a grammar. We're going to talk about a naive kind of breadth first search algorithm. We're going to talk about a cache-based method. And then finally, we're going to extend the cache-based method with equivalence reduction. So the grammar enumeration algorithm, the naive version, kind of goes like this. We're going to keep around a priority queue of what we'll call precursors. And then we're going to keep around a list of enumerated expressions. The first thing we're going to do is we're going to look at the starting non-terminal, and we're going to add any expressions that, so any terminals that appear on the right side of that, production. And we're also going to add any other productions to the precursors. So in this case, we add X to the list of expressions, and we add E union E to the priority queue. Now we're going to pop the precursor, and then we're going to consider all the possible substitutions into the non-terminals appearing in that precursor. If the substitution results in a precursor, we'll add that to the queue. Otherwise, we'll enumerate the expressions that we find. And then the idea is that we just kind of keep doing this in order to enumerate the expressions in the grammar. This has several problems. First of all, you'll notice that the ratio of precursors to expressions is very high So the priority queue grows really quickly. We're doing a lot of these substitutions. And what that really leads to is that we're scanning larger and larger precursors in order to do the substitution. And that's a source of inefficiency. So we're going to solve this using the cache-based method for enumerating grammars. What we're going to do is we're going to maintain a cache of enumerated expressions. We're going to partition the cache by size. Then we're going to enumerate expressions in size order and build larger expressions from smaller ones. For instance, if we want to enumerate the size 5 expressions from the grammar we saw before, we're going to assume that we have, sets of smaller expressions kind of laying around. In this case, there's one expression of size 1, 0 expressions of size 2, 1 expression of size 3. And so what we're going to do is we're going to look at all of the ways to sum to 4, because the 5th symbol is the union. And what this will do is we'll first combine expressions of size 1 with expressions of size 3 to get that expression. We'll combine expressions of size 2 with expressions of size 2. There are none. And then finally, we'll combine expressions of size 3 with expressions of size 1. So this is better because we're not kind of iterating over larger and larger precursors. The only thing that we're really like substituting into is the rules of the grammar, which are just, they don't grow. There's still a problem though. In particular, typically with grammars, the number of expressions of a given size that grows exponentially. And so we're going to mitigate this by only caching semantically distinct expressions. So this extends the cache method, but now in addition to maintaining a cache, we're also going to maintain a map of cached expressions to their normal form. And then if we generate an expression and we've encountered its normal form before, we're just going to throw it away. We're not going to add it to the cache. We're not going to enumerate it. And then we have different normal forms for kind of every expression type. For Boolean expressions, you can use something like DNF. For set expressions, actually, you can also use DNF because you can exploit the correspondence between like set algebra and Boolean algebra. For equality and disequality and inequality, you just want to make sure that the expression on the left is smaller than the expression on the right. And then, of course, if you have less than, you can always flip that to have greater than, etc. The other idea here is to do short circuiting for commutative operators. So basically, we can stop when the left side is larger than the right side. So we would, in the example before, we would look at expressions of size 1 and combine them with expressions of size 3, 2 with 2, but then we would stop once because 3 is bigger than 1. And because we have commutativity, we don't need to consider alternations there. And yeah, this will skip half the expressions, and we don't have to compute their normal forms. We don't even have to iterate over them. Okay, so now we can talk about some experimental results. We're going to compare the cache method with and without equivalence reduction. We're going to look at 8 benchmark protocols. And then for a given protocol, we look at multiple experiments using different holes. So this is the table kind of summarizing the results. The first thing to notice is that on the left side, those are the results for the method without equivalence reduction. And then on the right side are the results with equivalence reduction. In pink, what we'll notice is that the equivalence reduction obtains, pretty steep speed ups, as high as 20 times in some cases. We also notice that in blue, the method with equivalence reduction tends to generate far fewer expressions. For instance, 93,000 versus 3,000. And in the rightmost column, those two numbers, the pink one is the total time, and the one next to it is the time spent model checking. And so you'll notice that those numbers tend to be quite close to each other. So we would say that the time is dominated by model checking when we use the equivalence reduction. And then in contrast, if you look at the column underlined in orange, those numbers are not so close together. And so the time is actually dominated by other things, in particular, generating expressions. And then maybe one last thing to notice is that in the columns with the blue numbers, there are a lot more expressions that get generated than get model checked. So this kind of illustrates why it's so important to maintain these constraints on the uninterpreted functions to avoid model checking every single expression that we generate. So the full table is in the paper, not shown here, is that the tool can fill in as many as 8 holes. It can do both pre and post conditions. And the tool can synthesize expressions of size, 18. So that first expression that we saw on like the second slide, that has like a pretty large size. Oh, and in some cases, the tool is able to find expressions that are smaller than we were expecting. So one thing that I haven't mentioned so far is that model checking is only really applicable to finite state systems. So if you'll recall, the protocol synthesis task that I gave was take a sketch and a property and find a completion that satisfies the property. But really, there's 2 versions of this problem. In the first version, what we're going to do is we're going to fix the parameter values. So just assume, for instance, that there are 3 nodes participating in the protocol. And then if there are any infinite domain variables, we're just going to bound those. We're going to cap them. And then we're going to try and synthesize a protocol that satisfies the property under those assumptions, under the fixed parameter value and under the kind of capped variable domain. But the second version of the problem, which is what we really want to solve, is no, actually, I want a protocol and I want it to be correct no matter what the instantiation is. And yeah, if the variables have an infinite domain, they should be correct no matter what value the variable takes on from that infinite domain. What's nice is that solutions to version 1 often generalize to version 2, and you might call this like the small scope hypothesis, I've heard it called. And so the point I'm making here is that in that last table, those results that we obtained were obtained by synthesizing protocols that were only model checked for specific parameters, for instance, 3 nodes participating in the protocol, and for bounded variable domains. But what's critical is that we were actually able to kind of do a post-processing step where we used TLAPS to show that the synthesized protocols were actually correct for all parameter values and for the infinite domains. And we showed generalizability for all of the protocols that we synthesized. And to our knowledge, we're the first to synthesize protocols that generalize in this way to infinite state spaces. So just to conclude the talk, we talked about sketching and syntax-guided synthesis for distributed protocols. We talked about the learner verifier architecture for Segis. We talked about how we generalize counterexamples, and we kind of showed that this is really important so that you don't have to model check so many things. We talked about a cache-based method for enumerating expressions in a grammar, and then we extended that to kind of reduce the search space using normal forms. We saw some empirical evaluation results on 8 benchmarks, including a reconfigurable Raft variant. And then we talked about generalizability to infinite domains and all parameter instantiations. Great. Thank you guys so much. And I'm happy to take any questions. And I guess we can talk as well in general.
Derek, that was rad. Thank you so much. Maybe I'll start us out with a question, then I'm sure other people will have some. Are you familiar with Cole Vick's work on counterexample classes and classifying counterexamples, that sort of thing?
Yeah, roughly. Yeah. At a high level.
Oh, okay. Well, I mean, that kind of answers my question, but I was just kind of curious if you'd thought about whether anything like that might be useful in your context, right? I mean, you're kind of doing this generalization thing. To me, from the outside, it smells a bit like the type of problem that he was studying with the counterexample classification. Um, I don't know if like some formal theory of like counterexample classes unlocks some additional efficiency or something, but yeah, I mean, it might be worth exploring. This is very tenuous.
Yeah, no, that's a good idea. Basically, if you have a counterexample, like it was expensive to compute that thing, so
Yeah.
you should try to milk it as much as you can. Get as much information as you can out of the counterexample. We have some work related to this where basically, so we've done synthesis for kind of more explicit state models. Um, and one thing to notice about explicit state models is that they're equivalent if you rename the states.
Okay.
And you can actually exploit this idea to take a counterexample, which is like, it's a path through this graph. You can use that idea to actually generalize counterexamples and get like n factorial many counterexamples, which
Okay.
is great. So yeah, this is a good idea, and I guess
Cool.
we've kind of explored it a little bit, just not in the symbolic setting.
Yeah, that makes sense. I mean, I can ask more if other people are still thinking. Um, Realistically, like how complex of a distributed protocol do you think is sketchable with the kind of state of the art right now? Like, is Raft sort of? I mean, I don't know that there are more complicated things in Raft that we want to synthesize. I actually am not really sure in what context this, becomes like a practical concern. Um, but yeah, as somebody deep in the weeds, like where would you say kind of the cutoff is in terms of what can actually realistically be generated?
So I think right now the cap maybe isn't so much the complexity of the protocol, but maybe the bigger concern is how many holes do you have, and then how many expressions of a like how quickly does the number of expressions of size n grow? Um, because right now, like we're kind of handling this Raft protocol, and it has like 300 lines of TLA plus code. Obviously, we're not synthesizing all of those. We're synthesizing expressions for particular holes um, within those 300 lines of code. But like when we're model checking this Raft protocol, it has for very small parameter instantiations, say like 3 nodes, it has still like a million states. Um, so right now, I don't think the bottleneck is like how complicated the protocol is. I think it's how complicated is the sketch, basically. How many
Yeah, that
holes?
makes sense.
Yeah.
I had a question. So, is there an example of a protocol that is unsatisfiable? Like there is no value of a hole that can be generated that will satisfy the protocol. And what will be the behavior of your tool in that case?
Yeah, that's a really good question. So so here's a really unfortunate example. Let's say you just have one hole and the grammar is infinite. Um, and the property is something like false. Uh, Obviously, for such a simple, example, you would just say, "Oh, the property's false," so of course it's unrealizable. But in general, like that's not trivial to recognize at all. And right now we don't handle it basically. In principle, our tool, if you give it an unrealizable sketch, so an unrealizable sketch would be well, the sketch plus the property. If there's no completion of the sketch that satisfies the property, our tool will just kind of spin forever. We're working on, solving this right now. So future work. I guess like one naive way to maybe detect this is if you are enumerating expressions and you're trying to find an expression of size 20, but all of your expressions that you have laying around, so using the cache-based method, if all the expressions you have laying around are of size less than 10, then of course you can infer that you're not going to be able to find another expression. And then you could stop, I suppose. That's kind of a maybe a way to recognize unrealizable sketches.
Yeah. Is there a way to encode holes as SAT problems and like use a SAT solver as an oracle to tell you whether is it worthwhile to even search in that direction?
Yeah, again, so we're working on this problem right now, actually. We're actually using just another like an intermediate representation of the search space. Because right now, essentially the search space that we're using right now is just a grammar. And so like I think the issue that comes up basically, so if we just look at this picture, the issue that's kind of coming up is that the grammar enumerator knows nothing about the semantics of like counterexamples or constraints. So the work that we're doing right now is kind of more closely coupling these things using like tree
Yeah.
automata.
I could imagine if they share information, it could be helpful for both of them.
Yeah, yeah.
Cool. Like, like like if the counterexample generalizer knows about the grammar, it would be easier to search for a counterexample. And if the grammar knows about counterexample or maybe constraint, then it would be easier to enumerate grammar.
Yeah, yeah. Like one thing you can imagine doing is just to, I guess, give spoilers about the future work, is one thing you can imagine doing is taking like one of these constraints that we're computing and computing like an intermediate grammar that only has expressions that, you know, satisfy that constraint. And then you can imagine taking an intersection of these grammars. And these aren't full-blown context-free grammars. I didn't talk very much about this, but they're just like regular tree grammars. So they're actually closed under intersection. So this is kind of the idea that we're pursuing now.
Got it.
Yeah.
Do you think you really need to use a model checker? I mean, like if you just fuzzed for random inputs, would you find counterexamples slower than using a model checker in your context?
Okay, so that's, I think, yeah, that's a good question. So I know like the TLC model checker, it has different like parameters that you can give it. So it can of course do exhaustive model checking, but then yeah, I think there are options that are akin to fuzzing where it maybe it's not quite exhaustive, but it will, yeah, it'll do more branching.
But you do require your expression size to grow continuously, right? So if fuzzer might not be a good choice because a
So I guess
fuzzer can throw random size expressions at you.
I guess the thing that finds expressions and the thing that would do fuzzing, I think those are kind of decoupled, right? I think the suggestion was to replace the verifier with the fuzzer, or am I misunderstanding?
Yeah, I think that was, yeah, I think that's correct. Yeah. In other words, like make counterexamples using a randomized method that doesn't require computing like
Okay.
symbolic representation of the state space ahead of time, right?
I misunderstood the problem as saying the grammar enumerator. Instead of a grammar enumerator, have a fuzzer.
Yeah, I mean there are benefits to like the model checking approach, right? Like we have this paper in Usenix where we used exhaustive model checking with spin, and we were able to say that like within 100,000 caveats, like some change to the code ruled out some vulnerability. We wouldn't have been able to say something like that if it wasn't exhaustive. So I totally get the benefits of something exhaustive, but there's also like this downside of it being slow. So you could imagine kind of like the sketchy version. Sorry, I didn't mean to do a pun with sketching, but like you could imagine like shitty synthesis where instead of doing something that's formally justified, you just have like some random generation of traces and you try to find ones that are bad that way. And like, I don't know that it would be faster, but I would not be shocked if you told me that was faster, right? And so that's kind of, I guess, the root of my question is like, if you did something that was less mathematically justifiable to generate counterexamples, is it possible that you would actually generate them faster? I don't know if I honestly don't know if you would, but like I think it's worth at least like thinking about a little bit.
Yeah, no, that's a good idea because I mean, and they aren't like one or the other, right? You could imagine doing this like maybe more heuristic-y approach.
Sure.
Um, and like early on in the synthesis process, maybe it'll work really well because the protocols are in some sense more wrong because you don't have as much information that you're using to filter them.
Totally.
Um, and then, if that test passes, then you can do full-blown model checking, and that might be useful like later on in the search.
Yeah, that makes sense.
Yeah. Yeah, so that's a good idea. Yeah, we haven't done a lot of like um parameter tuning for like the TLC model checker either. So it's possible that like some options will allow us to find counterexamples quicker.
How do you like TLC? Like just from an ergonomic like user perspective, compared to spin or something. Right? Do you enjoy using it? I've never used it before.
Um, let's see. I'm trying to think back to the couple of experiences I've had with spin. I would say so just comparing those two, I prefer TLC to spin. Uh, yeah, I would rather use TLC than spin for sure. Yeah, to me, I think it's just the right tool for the job.
Okay.
Yeah. If I had to daily drive one or the other, though, I would pick TLC.
I've personally found that I think it's really easy to program things in Spin. However, where it becomes really frustrating is that the semantics are not actually like made especially clear anywhere. And so when you start writing, when you do metaprogramming, when you're like writing code that writes Spin or that interprets like Spin programs, you can
Mm,
find yourself just being driven up the fucking wall because like you don't actually know what some piece of code means. And
mm.
then sometimes the answer will be hidden in the spin book somewhere, but like very often the answer is you need to email Gerard Holtzman and he'll tell you, which is fine because he does answer his email very quickly, but it's not ideal, right? Like you'd really just rather know exact. And I guess that's an advantage of the TLA kind of ecosystem is that it's very clear cut what the code does.
Yeah, yeah. And so like yeah, that's what's nice is it has like very clear semantics. And even when the semantics are like really complicated, so for instance, TLA has these things called stuttering violations, which are a very particular type of liveness violation where basically you can't leave some state, but it's not a deadlock violation, it's a liveness violation because uh, you can leave the state, but there's no like fairness constraints that force you to leave the state. The point being that the semantics are very complicated, but if you like find the right place in the textbook, you know what it means. It's very clear what the semantics are. Yeah.
Okay, so I'll ask another like very vague question. Have you thought about kind of sketching based approaches to generating attacks against distributed protocols?
I have not. Yeah, I'm not super familiar with that literature. No.
I don't know that there is any literature on that, dude, but
Yeah.
but it is an interesting, thing. And Stavros's lab has done a bunch of cool, including with me, some, but like attack synthesis work, right? Like Lisa's done attack synthesis stuff. So I could see it being an interesting research direction to explore.
Yeah. So I guess like sketching is good for synthesizing programs. So if you can capture the attacker as a program, then
Right.
yeah, that would be a good idea.
So nice line of work would be to generate or synthesize a protocol and then generate an attack for that protocol.
Mm, yeah.
I'm kind of imagining something where you have like some threat model that specifies what the adversary is allowed to do, and you kind of are able to encode that using holes. Like the hole is like the, you know, gets filled in by a grammar capturing like all the shit that the attacker's allowed to do. And then there are different holes in the different spots where the attacker's allowed to do things. And now you have a sketching problem. Again, like I've literally never done sketching, but just kind of from having read a few papers and listened to your talk, that
Yeah.
feels like potentially something that could be formulated. And yeah, I don't know that you'll get better results than using other techniques for finding attacks, but it's theoretically kind of interesting. And I could see it being a nice complement to a work like this.
Yeah, that does sound promising. Yeah.
Cool. Any other questions from the audience, or should we call it a little early today?
Oh, I have probably what's a really basic question. I was just wondering if you benchmarked how this compares to just like truly random search of the syntax space. If you like removed the counterexample learning from this.
Oh, interesting. Right. So I guess, so are you suggesting like sampling from the grammar?
Yeah.
Yeah. We haven't tried that. Yeah, I don't. There are a lot of expressions, I guess. So I imagine that that would not work very well. Like if, for instance, if the smallest expression is of size n, and you're just randomly sampling, yeah, I mean, it's gonna be like order of 2 to the n things that you're probably gonna have to sample before you find the right thing.
Yeah. I'd be kind of curious just like how much of the search space each of these constraints that are generalized are like cutting off.
Yeah, I guess we can maybe estimate that if we look at this results table. So if we just look at like the first row, this decentralized lock row. Yeah, so you'll notice that only 136 things were model checked. So what that means is that we only generated kind of 136 of these constraints. And, we generated 93,000 expressions. And basically, all but 136 of those were eliminated using one of the constraints we found. I think that's a fair interpretation of that number. So I think the answer to your question is, yeah, it works really well. It works like surprisingly well, I would say.
That's really cool.
Yeah. Yeah, when I first learned about like counterexample guided inductive synthesis, I was like, that works. Like, yeah, it works because you can prune the search space a lot using counterexamples. And I guess to give more intuition for why you can eliminate so many counterexamples is that if you go to this generalization slide, like that very simple constraint, it says, under the case where GoBor is the empty set and n is equal to a, the expression cannot evaluate to the empty or the singleton set a. Like that is a really simple constraint and it excludes a lot of things in the search space. Yeah. So that's kind of like why it works so well, I think. Yeah.
Okay, I have a really basic question. Probably like when you are checking this constraint, I assume you like get some expression for age, and then you're like, I guess I don't really understand how TLA plus works very well here. You're like evaluating that expression on the inputs you've learned from the counterexample?
Yeah, so by the time that we're doing constraint checking, basically TLA plus doesn't exist. The constraints are again just these like these disjunctions. So you'll notice like the counterexample doesn't exist anywhere. It's just the only free kind of variable here is h. So yeah, in order to check like future completions, you just take the expression that you picked for H, you plug it in, and you just evaluate that expression.
So could you go back to that previous slide?
Yeah.
Like in the next, say I like for my expression for H with something like next, which is like an or, like, so like how do you evaluate that? You have to like, do you evaluate like next is something or something else? Like, do you have to evaluate both of those or branches to know that definitively that it won't output the counterexample?
So if H is a disjunction, then I guess it's just any other expression, right? In that sense, the disjunction appearing in H, it's very different from, I think well, I guess it's not different, but it's a little bit different than the disjunction appearing in next.
Okay, cool.
But yeah, if you have H and it's a disjunction, still your constraint is just going to be yeah, I mean, when you plug that disjunction into the constraint, it's still going to be something that you can evaluate, and it just resolves to a constant.
Gotcha. Okay, thanks.
Yeah, thanks for the questions.
Cool. Derek, this was super cool. Thank you for talking to us. Is it okay with you if I put the recording online afterward? Would you prefer I don't? How do you feel about that?
I think that's fine. I don't think I've said anything that will get me in trouble. So
Okay.
yeah, it'll be
If
okay.
you change your mind, let me know and I'll take it down. But sometimes these things do surprisingly well. Genuinely, I mean surprisingly. Like I can never predict what's going to do well online. I think Carlo Anguli's homotopy type theory talk has like hundreds of views, which is wild because I didn't know there were hundreds of people who knew what homotopy type theory was. But so you never really know. But yeah, really appreciate your time. This was a fun one, and hopefully we'll have you back when you whether write the next paper, whether it's doing attacks or something else.
All right. Yeah. Thank you so much, Max, and thanks everyone for your attendance.
Okay, adios.
Yeah, thank you.